Hello, welcome back to another video. Today we're going to discuss differentiation, which is chapter 5 of the book. And here we go, let's start. Let me just see if I'm recording again. Okay. Now we define the derivative of a real function like this. Phi t equals f of t minus f of x over t minus x. And we say f prime of x, which is the derivative of f, is equal to the limit as t goes to x of phi t. So basically, this is really similar to the other formula where you take f of x plus h minus f of x over h. Just imagine replacing t with x plus h. It will give you the same thing. And we know if t equals x plus h, as t goes to x, x plus h goes to 0. So it's basically the same thing. And this is basically the slope of the function at that given point. Because you're taking two separate points, which is and taking their differences, which is the rise, and then you're taking the run and you're making them go infinitely small, and that's going to be the slope at that point, if you look at it visually, which you've probably seen in calculus. You obviously have seen it in calculus. Now we say that f is differentiable at x if f prime of x exists at a particular point x. And we can also say it's differentiable on a set E. Now, we have we have other definitions too, because we can have right-handed derivatives and left-handed derivatives if you take the limit from the right and the left, basically. So you can imagine the function absolute value of x. The right hand derivative at x equals 0 is 1. The left hand derivative at x equals 0 is negative 1. And since they're not equal, the derivative doesn't exist. Now, we have the following theorem. Let f be defined on AB. If f is differentiable at a point x in AB, then f is continuous at x. Now, the proof is as follows. We know that f of t minus f of x is basically f of t minus f of x over t minus x times t minus x. And as this goes to 0, we can take this to be f prime of x, and this is 0. So this is basically equal to 0. So the limit as t goes to x of f of t is equal to f of x. That's basically what it's saying. So which shows that f is continuous at x. Now, there's also another interesting proof for the continuity of derivatives, which is related to connectedness. We'll see it later on. It's basically the intermediate value theorem, but for derivatives, which we're going to see. And the strategy here is to relate it to the derivative and show that it goes to 0. And since it goes to 0, we know that this thing is a limit of this. Now, theorem 5.3. Suppose f and g are functions defined on AB and differentiable at some x in AB, then f plus g, f times g, and f over g, with g of x not equal to 0, are all differentiable at x. And we have the following properties. Fg prime is going to give you f prime g plus fg prime, and f over g prime is going to give you gf prime minus g prime f over g squared. Now, the proof is pretty straightforward here. It's basically you're going to take the differences of the functions times the other function and adding them together. And since you know the differences are basically the derivative times the run, which is t minus x, you can relate it to the derivative. So basically here you have this. If you want to show how the strategy works, you have this. F of t is equal to f of t times g of t minus g of x plus g of x times f of t minus f of x. And this f of t times g of x and this g of x times f of t is going to go away. And we're just going to be left with f of t times g of t minus g of x times f of x, which is the same thing as this. And we can use this property related to the derivatives and show that the derivatives are equal. Just divide each side by t minus x, and you're going to get the derivative of each function. So h prime is going to be equal to f times g prime plus g times f prime. Now, for this formula over here is very similar. You're going to write it in a way so that you can make the differences of them multiply together, and so you can get the concept of the derivative working. Because if you want to relate it to the derivative, we want to take differences like this. That's the strategy, right? And if we take differences like this, uh, if you wanted to make it equal to this, you're forced to divide by g of t times g of x over here. And this thing over here, this left hand side will give you the right hand side over here if you expand the components. And as t goes to x, this is going to become g squared, this is going to become the derivative of f, this is going to become the derivative of g, and this is going to become the derivative of h. So we're going to have f over g prime is equal to g f prime minus g prime f over g squared. Now, if we use these properties, we're going to get that derivative of any constant function is 0. It's obvious because if you want to explain it, the derivative of 1, for example, over here, if you want to take the derivative of 1, it's just 2 over 2, right? So it's going to be, or I can just take it over here. The derivative of 1 times 1 is going to be the derivative of 1 times 1 plus the derivative of 1 times 1 prime. So the derivative of 1 is equal to 2 times the derivative of 1, right? And since that's only possible if 1 is 0, that means the derivative of 1 is 0. And since you can multiply it by any other constant, the derivative of other constants are also 0. For the identity function f of x equals x, we have f prime of x equals 1. And that's pretty straightforward if you take x times 1 over here. So you're going to get x prime. Okay, no, not really. But the way you can show that it's 1, it's actually, you can just take the definition of the derivative itself, right? Just replace it with t over here, replace it with x, you're going to get t minus x over t minus x, and no matter the limit, it will give you the 1. And if you repeat it, of course, you're going to get the famous derivative rule for polynomials, which is f prime of x equals n times x to the n minus 1. Now we have the chain rule, as you've seen it in calculus. We want to prove it. It has a really similar strategy to this. We want to find differences and combine them together. So we want to show that h prime of x is equal to g prime of f of x times f prime of x whenever g of t is equal to g of f of t. And the way we do this, y equals f of x, and f of t minus f of x is equal to t minus x times f prime of x plus u of t. What that means, basically, you divide both sides on with t minus x. You're going to get f of t minus f of x over t minus x. And this thing, as t approaches x, it becomes a derivative. So, but it isn't necessarily approaching that thing, so, right? So it's going to give the derivative plus another thing that we don't really know. So we're going to add it just in case, right? Same thing for here. That's what we're doing. But now what we're doing is that we're taking g of s minus g of y instead of t and x. Basically what we're doing, as v of s goes to 0. And now we set s equals f of t. So we're finding differences and setting different variables that are going to be nested together. So h of t minus h of x is going to be g of t minus g of f of x, g of f of t minus g of f of x. And basically it's going to be equal to this thing, right? So we're just replacing s with f of t and y with f of x. And we're going to get this. And now we substitute f of t minus f of x equals t minus x times f prime of x plus u of t. And we're going to get that, so just replace it over here. And you can just divide this on both sides to make it become like this, and you're going to get this over here. Now as t goes to x and s goes to y, these are going to become 0 because they're the remainder terms, right? And when we let them go to 0, the limit becomes a derivative, so we don't really need them anymore. Thus, a limit becomes h prime of x equals g prime of y times f prime of x equals g prime of f of x times f prime of x. So that completes the proof. We have the following examples. Consider the function f of x equals x sine of 1 over x not equal to 0, and 0 at x equals 0. We take the derivative. Just keep in mind that the derivative of sine of x equals cosine of x, and the derivative of cosine of x is equal to negative sine of x. So if you use the chain rule over here, you're going to get that x times sine, the derivative of sine of 1 over x, which is going to be x times cosine of 1 over x times the derivative of the inside, because that's the chain rule, times negative 1 over x squared is going to give you negative 1x over cosine, negative 1 over x times cosine of 1 over x. And if we take the derivative of x and then multiply by sine of x, we're just going to get the derivative of sine of 1 over x, because the derivative of x is 1. So we're going to get this expression for f prime of x. Now at x equals 0, you can't really find the derivative over here, because it's going to be sine of 1 over 0, which doesn't really make sense. And over here is going to be 1 over 0 times this. Instead, we use the definition of the derivative to examine it further. We're going to get f of t minus f of 0 equals over t minus 0, which is going to give you t sine of 1 over t minus 0 over t, which is going to give you sine of 1 over t. And as t goes to 0, we know that this limit doesn't exist, so f prime of 0 does not exist. Now here it's interesting, because here the f prime of 0 does exist, but it's not continuous. So if you take the derivative over here, it's going to give you this, and use the definition of the derivative, it's going to give you this, and we know this is less than or equal to t. As t goes to 0, we have f prime of 0 equals 0, because the absolute value of the derivative is less than or equal to 0, so it means that it is equal to 0. But notice it's not continuous, because the term cosine of 1 over x and f prime of x oscillates without approaching a limit as x goes to 0 over here, as you see. Now we have the mean value theorems. Let f be a real valid function. Now we're talking about local maximums, minimums, extremums. So it's when you have 1 point less than a point or 1 point greater than a point in some neighborhood, and that's how we define maximums or minimums. And we're going to get f of q is less than or equal to f of p whenever the distance between p and q is less than delta. That's a local minimum and a local maximum. Now we have the following theorem. Let f be defined on AB if f has a local maximum at some x in AB, and f prime of x exists, and f prime of x is equal to 0. Basically what you're going to do over here for this interval, the strategy is taking intervals before and after and showing that one is greater than 0 and one is less than 0, and we know when the derivative exists is continuous, so we know that at one point there's going to be the derivative being 0. That's what we're doing. So f of t is less than or equal to f of x for this point. That means this is greater than 0, and that means this is less than or equal to 0 for this interval when f of t is less than or equal to f of x. That means there's a point that when we combine the two inequalities, we have f prime of x equals 0. Now we have the following very important theorem that you've seen in calculus. If f and g are continuous on AB and differentiable on AB, then there exists a point x in AB such that f of b minus f of a times g prime of x is equal to g of b minus g of a times f prime of x. Now here again the strategy is to take differences of the functions and multiply them together, and basically when you're doing this, when you evaluate them on both endpoints, you're going to see that both endpoints are actually equal, like this, you see. h of a is equal to f of b times g of a minus f of a times g of b is equal to h of b. Now, we want to find h prime of x is equal to 0. Why we want to find this? Because we want to show that this has a maximum or a minimum. Um, um, Wait a second. Let me just think about this. Yeah, basically we want to show that h prime of t is equal to 0 so that we can get this expression. Because this expression, when you take this on the other side, when this is 0, you're going to get this expression. That's also another part of the strategy, right? If you want to construct this expression, you want to take them, you want to subtract them so that when it's 0, you can find a maximum, which is going to give you this thing, this expression over here. So we want to find h prime of x equals 0. When h is constant, it's obviously 0. Otherwise, h either attains a maximum or a minimum at some x and ab. By theorem 5, because the both endpoints are equal, so we know that it achieves a maximum in that before coming back to the other endpoint, right? It either achieves a maximum or a minimum. So we know that h prime of x is equal to 0 at such a point, and it gives you this. And we have the mean value theorem, and this follows by choosing g of t is equal to t in this generalized mean value theorem. And basically now we have another theorem which is about monotonicity and the sign of derivatives. Suppose f is differentiable on AB. If f prime of x is greater than or equal to 0 for all x in AB, then f is monotonically increasing. If f prime of x equals 0 for all x in AB, then f is constant, and if f prime of x is less than or equal to 0 for all x in AB, then f is monotonically decreasing. And it follows from the mean value theorem, right? Why? Because if you take the differences between 2 points, you're going to get, it's going to give you this. And we know that this is greater than 0, and this is greater than 0. So this divided by this is greater than 0. That means this is greater than 0 when it's monotonically increasing, and it's less than 0 when it's monotonically decreasing, or equal to 0. It could also be equal to 0 for some points, right? Because it could keep constant, because monotonically increasing and decreasing functions also include constant functions. Now we have the continuity of the derivative. One important property of the derivative defined on an interval is that they satisfy the intermediate value property. And we want to show this. Is this actually called Darboux theorem? Let me just make sure. I'm not sure. Yeah, it's called the Darboux theorem. Or Darboux. Okay. So let f be a real valued function differentiable on AB. Suppose f prime of A is less than lambda is less than f prime of B. Then there exists x in AB such that f prime of x is equal to lambda. A similar conclusion holds if f prime of A is greater than f prime of B. Now, the strategy over here, we want to take g of t is equal to f of t minus lambda t. Why? Because if you take the derivatives, this is going to become minus lambda. And we want to evaluate this function at both endpoints, at f prime of A and f prime of B. And since we know that this is between them, we can show that one is less than 0, one is greater than 0, and use the mean value theorem to find the find that it achieves a minimum or a maximum. And that's basically the strategy, right? We want to get to the conclusion that it achieves this, so that means it's between this. And how we do that is we set this equality over here and we differentiate. So g prime of a is equal to f prime of a minus lambda is less than 0. So there exists T1 and AB with GT1 less than GA. Why? Because if you take GT1 minus G of A over T1 minus A, it's going to give you the derivative of the derivative it's going to give you the derivative at some points between A and T1. And we know that that derivative is going to be less than 0 because we showed that f prime of A is less than 0. So in that neighborhood, it's going to be less than 0. Just to say it more clearly, yeah, exactly. So the derivative is going to be less than 0, so you can backtrack and get it to become this expression over here. And here g prime of b is greater than 0. And similarly here, you can take g of t2 minus g of b over t2 minus b. Sorry, over b minus t2. No, actually it doesn't matter because you're taking the same differences in both numerator and denominator. So g of t of 2 minus g of b over t of 2 minus b, and that's a derivative at some points between b and t of 2, and we know that's greater than 0. Actually no. Yeah, that's greater than 0. So now, if you multiply this negative term of the denominator over here, it's going to flip signs. So this greater than 0 is going to become less than 0, and you take it on both sides, and you're going to get g of 2 is less than g of b. Hence, g attains its minimum at some point x in AB. Okay. So this is less than g of a. This is less than g of b. I think what you do here is you take the differences between these two inequalities and divide it by b minus a. Exactly, yeah. You divide by b minus a, and that's going to give you that this thing, these things, okay. Wait a second. Let me just read the book. Hold on a second. I'll be back. I'll be back. Okay, so I'm back. Let me just see if I'm recording. Okay. So the strategy here is to show that neither g of a nor g of b are the minimums, because there's always some t2 and t1 that whose g is less than those. So that means the minimum is achieved not on ab but somewhere between ab. So that means g prime of x equals 0 at some points, and that means that f prime of x is equal to lambda. And we have the following corollary. If f is differentiable on AB, then f prime cannot have simple discontinuities on AB. However, f prime may still have discontinuities of the second kind. And why? Because we just showed that the right hand and the left hand limits exist, because derivatives imply connectedness. Now for L'Hopital's rule. This is a very important rule that you've seen in calculus. Let f and g be real valued functions differentiable on AB with g prime of x not equal to 0 for all x in AB, where negative infinity is less than or equal to a, less than b, less than or equal to infinity. And suppose f prime of x over g prime of x goes to a as x goes to a. And we have one of the following. F of x goes to 0 and g of x goes to 0 as x goes to a, or g of x goes to infinity as x goes to a. Then f of x over g of x goes to a as x goes to a. So you've seen this in another way in calculus. So it's basically the other way around. They say if f of x over g of x goes, if you have f of x over g of x, and if it's 0 over 0 or infinity over infinity, then you have that it's equal to f prime of x over g prime of x. It's basically the same thing. You can just backtrack your way and show that these are the same thing. So you're just coming in from the derivatives instead of from the actual functions. And another key thing to notice is that it's only g of x that goes to infinity. You don't need f of x to go to infinity. That's a really interesting property. And the strategy here is to take this over here less than some number r, and we can, since we know that f prime of x, you can use the mean value theorem to say that it's a derivative between 2 points. It's actually the difference between 2 points divided by the difference of the run, and you can use that f of b minus f of a over b minus a instead of the f prime of x definition, right? And like that, since it's less than r, you can just replace it and expand some interesting properties with it, and show that this thing over here, you can isolate it to become the f of I over g of y, and it's going to be less or equal to r less than q. So you want to take this to be less than some value, and show that this is also less than that value, to show that they go to the same thing. Let's read the proof now. Okay. First, assume negative infinity less than a less than infinity. Choose a real number q greater than a, and then select r such that a is less than r less than q. We know that this happens, and we know that f prime of x over g prime of x is less than r for all x in AC when C is in AB. And if a is less than x less than y less than c, we have that this is equal to this by the mean value theorem is less than r, and f of x and g of x go to 0 as we let x go to 0, and we're left with this. And notice the second part of the proof is to, instead of taking it less than a value, take it to be greater than a value, and put like 2 bounds on them to show that they go to the same thing. Now for case 2, it's when g of x goes to infinity as x goes to a. So here we can choose C1 and AY such that g of x is greater than gy and g of x is greater than 0. Because we know that it goes to infinity, so we can take values greater than g of y, because there are infinitely many values above it. So we can multiply the equation 18 with g of x minus gy over g of x, again like using the property of differences, and you're going to get that it's going to give you this, because we know that f prime basically okay, we're going to multiply it by this, right? So it's going to give you f of y minus f of x over g of x, because this is going to go away with this, right? And we know that one of the terms goes to 0, and we're just left with this f of x over g of x is less than r minus r times g of y over g of x plus f of y. Sorry, yeah, the f of y over g of x goes to on the other side. It doesn't go to 0, it goes on the other side, and we're left with this over here. As g of x goes to infinity, all this goes to 0, and we're left with that f of x over g of x is less than q. And you can do this with, on the other way, say this is greater than some value p, and this proves L'Hopital's rule. Now higher order derivatives, basically when you apply derivatives multiple times, and we have Taylor's theorem. Let f be a real valued function on AB, and let n be a positive integer. Suppose f of f differentiated n minus 1 times is continuous on AB, and f of n t exists for every t in AB. Let alpha and beta be distinct points in AB, and define the Taylor polynomial of degree n minus 1 centered at alpha by this thing over here. And there exists a point x between alpha and beta such that f of b is equal to p of f of beta is equal to p of beta plus fnx over n factorial times beta minus alpha to the n. And the proof here is that you take f of beta is equal to p of beta plus m times beta minus alpha n. And we want to show that this m is actually this thing over here. And how we do this is that we take the derivatives multiple times and show that these derivatives go to 0, and we're just left with this term over here for some x. So take, so this is actually equal to, we define g of t equals f of t minus p of t minus this. So basically this minus this for some point t. So g of beta is going to give you 0, right? Okay. Now take the derivative n times. You're going to get that this is equal to because p of t over here is only, it goes up to n minus 1 value. So if you differentiated n times, all of them will go to, all of the values will go to 0, because you're just left with constants and you're taking their derivatives. So you're going to get gn of t is equal to fn of t minus n factorial m, because that's when you take the derivative n times, you're going to be left with n factorial. Each time you're reducing n and multiplying by n times n minus 1 times n minus 2, etc. And what we want to do is that we want to show that gn of x is equal to 0 And because if it's equal to 0, that means fn of t is equal to n factorial m, and we're going to get that m is equal to fn t over n factorial for some x, which is basically what we want to prove. We want to prove that m is equal to this term over here. And how we do this right now, I know that the kth derivative of p alpha is the same thing as the kth derivative of f alpha. Um, um, give me a second. Okay, so I'm back. Yeah, okay. So the reason why kth derivative of p alpha is equal to kth derivative of f alpha is because take this over here. If you take the kth derivative, you're going to be left with this thing over here times this k times all the way to 1. So this and this will cancel with the derivatives, and you're going to be left with this term and other terms. But other terms have this t minus alpha, and if you set it to be alpha, you're just going to be, all the other terms will go to 0, and you're just left with this term over here. So that's why kth derivative of p alpha is equal to kth derivative of f alpha for k equals 0 to n minus 1. So that means that if we take g of alpha, we're going to be left that all these derivatives will go to 0. Why? Because g prime of t is equal to f prime of t minus p prime of t minus this, the derivative of this, apply alpha to them, these things are equal, it goes to 0, and this is going to be n times m times t minus alpha, put alpha, this also goes to 0, and so you're going to get that all the derivatives, no matter which order of alpha that you take, is going to be equal to 0. And we know that another part of the strategy is that we chose that not only g alpha is equal to 0, but g beta is also equal to 0. Because g beta is equal to f of b minus this, which is going to give you 0. By the mean value theorem, there exists x1 between alpha and beta such that j prime of x1 is equal to 0. And since g prime of alpha is equal to 0, we apply the mean value theorem again to get find x2 between alpha and x1 such that this is equal to 0. That means this is the nth derivative of g of xn is equal to 0, which means that the nth derivative of xn of f of xn is equal to n factorial m, and divide n factorial on both sides, and you're going to get that m is equal to nth derivative of f of xn divided by n factorial. Now we can also differentiate with complex functions and vector valued functions. For example, like this, you get f of t equals f1 of t plus I f2 of t. The derivative is just going to be f prime of x equals f1 prime of x plus I f2 prime of x, because the I is a constant. and uh, we define the derivative of vector valued functions like this. We take the norm before because we want to make sure that this thing uh, and this thing are the same thing, not just their absolute values. So that's why we put both of them in the absolute value. And we can show that taking the derivative of the vector valued function is like taking the derivative of its components. Now, one thing that's interesting is that the mean value theorem and the L'Hopital's rule may not always work for vector valued functions. For complex functions. It works for real vector valued functions, but not for complex functions. So, for example, we take f of x equals e to the ix, which is cosine of x plus I sine of x. F of 2 pi minus f of 0 is 1 minus 1 equals 0. And we know f prime of x is equal to I e to the ix. And the absolute value of this is going to give you 1. And we know if we use the mean value theorem, there must be something that has its derivative to be 0, because the difference of this is 0 divided by 2 pi is still going to remain 0. But we know that the absolute value of all these things is 1, so it can't be 0. So that means it fails to work. Now for L'Hopital's rule, we can, this thing over here, if you take these two functions, limit as x goes to 0 of f of x over g of x is equal to 1. And the reason why is that basically this is going to be x over x plus x squared times e to the 1 over x squared. Multiply both the numerator and the denominator by 1 over x, you're going to get that it's equal to 1 over 1 plus x times e to the 1 over x squared. And we know that this thing, its absolute value is equal to 1, and it's multiplied by x squared. Take the division, it's obviously going to be greater than 1, but when you let it go to 0, this term goes to 0, and you're just left with x over x, which gives you 1. Now, g prime of x is equal to this if you differentiate, and you can use a triangle inequality here and show that the absolute value of g prime of x is greater than 2x minus 2I over x minus 1 is greater than 2 over x minus 1. Again, by the triangle inequality. And now if you do the absolute value of f prime of x over g prime of x is going to give you 1 over the absolute value of g prime of x, because f prime of x is equal to 1, and it's just the inverse of this, and you flip the sign, so you're going to get 1 over the absolute value of g prime of x is less than or equal to x over 2 minus x. And as this goes to 0, this goes to 0. So this contradicts the L'Hopital's rule, because this goes to 1, this goes to 0. But it's supposed to go to the same thing. But one thing that does work for vector valued functions is the mean value theorem, and we write it as this, and we use a supremum of the norm over here because we're talking about vectors. And now we have the following theorem. Let f be a continuous mapping from AB into Rk that is differentiable on AB. Then there exists some x in AB such that f of b minus f of a its absolute value is less than or equal to b minus a times the absolute value of f prime of x. The strategy here is to take z to be the difference of these two, and then use the dot product and show that relate this dot product to the norm, and show that the norm of this is less than the norm of this. And one way that this is logical is because the difference of this, if you take the dot product with something, you can find, normally when you take the dot product with something, there's a way to find the minimum or the maximum, right? So that's also part of the strategy that we're doing here. So let phi t equals z dot ffd. So phi of b minus phi of a is equal to b minus a phi prime of x, because this is a real valued function. So it has a, you can use a mean value theorem here. So it's equal to b minus a times z dot f prime of x, because the derivative also works for the dot product, and z is a constant, so we just take the derivative of this. So, but notice that means that this thing over here is equal to z dot f of v minus z dot f of a. Because we're just taking the definition of this, right? So replace t with b and a over here, you're going to get this. Take the difference. And you can because you can factor out the dot product, so it's going to be z dot f of b minus f of a, but f of b minus f of a is z, so it's just going to be z dot z, which is norm of z squared. So you can just replace this over here. We know that z squared over here is equal to this thing over here, and this thing over here is less than this thing over here, because multiplying the norms by the Cauchy-Schwarz inequality is greater than doing the dot products of the thing. Divide by both sides by the norm of z, and you're going to get the property that the norm of f of b minus f of a is less than or equal to b minus a times the norm of f prime of x. Now we get to the exercises. Some exercises that I found interesting to show in the video is that you can find f prime of x like this, and it's basically with L'Hopital's rule, right? Because both of these go to 0. Take the derivative, you're going to be left with f prime of x plus h plus f prime of x minus h minus 2f prime of x over 2h. And you can separate them, and you're going to get that is equal to 2 times the derivative, the 2 times the definition of the limit of the derivative divided by 2, and you're going to get that is equal to f prime prime of x. Actually, wait. Okay, I had to stop recording. Okay, this is wrong over here. This is just the copy pasted of this without the prime over it. This is the correct version. So let me pull up the notebook over here. Okay, so we have limit as x goes to 0, f of x plus h, sorry, h goes to 0. minus f of x minus h minus 2f of x over h squared. Notice all this will go to 0 because this will become 2f of x. So this is plus over here. 2f of x minus 2f of x is 0 and h squared is 0. So take the derivative, f prime of x plus h plus f prime of x minus h. And basically what you can do here is you can split this f prime of x over here, minus f prime of x plus this minus f prime of x. And notice this is just over 2h. This is equal to, because now you're using this definition of the derivative over here. So basically, let me just write it another way. This is 1/2 times this over h plus this over h times 1/2. This is the derivative of f prime of x. So f prime prime of x. So 1/2 f prime prime of x. And this is also the derivative of f prime prime of x. So adding these two halves together, you're going to get that is equal to f prime prime of x, basically. Okay. Now, another interesting exercise. This was exercise 15. Okay. So let me just erase this. Okay, so let me just split the screen. We want to show that for twice differentiable function on a to infinity, when we have the least upper bounds of f of x, f prime of x, and f prime prime of x to be m0, m1, and m2, we have m1 squared is less than or equal to 4m0, m2. And how we do this is like this. By Taylor's theorem, can take f of x plus 2h is equal to f of x plus f prime of x times 2h plus f prime prime of x over 2 times 4h squared, because it's 2h squared this time. First, actually, this is going to be zeta over here. Right. So if you take all this on the other side, you're going to get this expression over here. Now, if you take the norm, this expression over here, this is going to be basically take the absolute value over here. It's going to be less than or equal to, let me erase this. This is going to be less than or equal to this f of x plus 2h minus f of x over 2h plus h times f prime prime of zeta. This is less than or equal to m2. Now this and this, you can take this to be less than or equal to f of x plus 2h, its an absolute value, plus the absolute value of f of x over 2h. And this is less than or equal to 2 times m naught over 2h, and we're just going to get it to be m naught over h. So we're going to get this inequality over here. And now what you want to do, now is multiply this together, and we're going to get that h m2 plus m naught h m2 plus m naught h. It's going to give you h squared m2 squared plus m2 m naught plus m naught m2 plus m naught squared over h squared. And now what you do over here, you're going to get let h is equal to the square root of m naught over m2 basically. So this is going to give you m naught times m2, and this is going to give you m naught squared over m naught over m2, which is going to give you m naught over m2 again. So you're going to get that this is equal to 4 m naught m2, which proves the theorem. And if you want to get an equality, you can use this function over here. And we call up x a fixed point of f if f of x equal to x. If f is differentiable and f prime of t is not equal to 1 for every real t, prove that f has one fixed point. And this proof is really straightforward. Basically, suppose two fixed points. T1, T2. So we know that f of T1 minus f of T2 over T1 minus T2 will give you the derivative for a point x. But notice this is the same thing as this, so it becomes 1. So if the derivative is 1, that means it could have more than one fixed point. So if f prime of t is not equal to 1 for every real t, prove that f has at most there's supposed to be at most here. And to show that this has no fixed points, let f of t equals t. So that means 0 is equal to 1 over 1 plus e to the t, but we know that this denominator is always a number, and we know 1 divided by something will never give you 0. And we know it's between 0 and 1, because take the derivative. It's going to be 1 plus negative 1 over 1 plus e to the t squared times e to the t, and this is always going to be a value between 0 and 1, right? And there's also an exercise for Newton's method, and you've seen it in calculus. Basically, if you forgot, you can look it up. It's basically when you take a value close to a root you're trying to approximate, take the slope, take the intersection with the x-axis with that tangent, and continue the process to get better approximations. But notice it doesn't always work for every function. For example, for cube root of x, it could shoot you off very far off from the value you're trying to approximate. And there's also initial value problems related to differential equations. It's basically when you have f prime of xy for each point xy, and you're just constantly applying them again to get the derivatives at each of these points. And they're really interesting exercises. You can look them up if you want to. And that's about it for this video. I hope you really enjoyed it, and stay tuned for the next one. I'll see you later. Bye.